Hello everyone, myself Neeraj Undirwadi. Today I am presenting a topic which is fields and radiation of a localized oscillating source. So in general, radiation can be thought as an irreversible transport of energy out to infinity by fields due to the acceleration of charges. In other words, accelerated charges create electromagnetic radiation fields that carry energy from one point in space to another in an irreversible fashion. Irreversible simply that there is no definable way to extract the energy back from the wave. That is, the wave radiated towards outward does not come back in. So let's suppose we have a radiation source which is localized somewhere near the origin of our choice of coordinate system. This source emits electromagnetic radiation fields that carry energy outwards. Therefore, we could also think about the electromagnetic power that is carried by this wave. Suppose we have to calculate the electromagnetic power through a surface as shown in figure. The electromagnetic power is simply defined as the flux of the Poynting vector S P with respect to r and time, which is equal to 1 by mu naught integration 0 to infinity E into E cross B. Since the Poynting vector is a time dependent quantity, this is time dependent quantity, the electromagnetic power is also time dependent quantity. Now at large distance r is to infinity, the electromagnetic power due to the source at some retarded time t0 equal to t minus r by c is defined as the radiated power. This retarded time means this is the delay of time or very slow time. This is given as p retarded, which is t0 equal to limit of r to infinity. Then potential due to oscillating electric dipole. Calculating the potential due to an electric dipole is the primary step in order to able tell anything about the radiation mathematically. Our task is to calculate the potential and then derive the fields due to an oscillating electric dipole. Here we consider electric dipole where positive q charge and negative q charge. Then we have to calculate the potential at point P, which is at a vector distance r. This distance is d by 2, this distance is d by 2. Suppose at time t the charges on a sphere is qt and that on the b sphere is minus qt. Also suppose that by some method we are able to change the signs of these two charges simultaneously at regular intervals. This will essentially result in an oscillating electric dipole qt equal to q naught cos of omega t, where q naught is the amplitude and omega t is the frequency. The oscillating dipole moment will be given as p of t equal to finally p naught cos of omega t. We have a reference point P which has the position vector r. This point P is often called as field point. We can now calculate the retarded scalar potential at P as flux with respect to vector r with respect to time equal to 1 by 4 by epsilon naught. This is for positive q sphere and this is for negative q sphere. Since distance is d by 2, so calculate that in equation r plus and r minus, given as r plus minus equal to r square plus d by 2 square minus plus rd cos theta. Here r is the magnitude of the position vector r. In order to further simplify our approach, we shall make three assumptions which will convert the physical dipole considered to a perfect dipole. Approximation 1. The length of the dipole is extremely small as compared for the position of field point, that is d by r. From figure, the distance of uh, this dipole is very small as compared to position vector r. This is our first assumption. Second approximation is the length of dipole is extremely small as compared wavelength of emitted radiation. That is the this length, which is the distance from dipole, is very less than the emitting radiation. And approximation 3 is r is to infinity, that is the field vector point is at infinity where we have calculate radiation. Applying approximation 1 to equation 4, then we got r of 1 minus d r cos theta. By binomial approximation, r plus minus equal to r of this g will also reciprocal of equation, and applying the binomial approximation, इसका इन्वर्स करेंगे 1/r इक्वल टू 1/r1 प्लस माइनस डी ऑफ r cos theta. Now calculate these two terms for positive q charge and negative q charge in equation 3. Now equation 6 we have cos of omega t minus r by c. फिर इसको अरेंज करके r प्लस माइनस की वैल्यू यहाँ पुट करेंगे. फाइनली cos of omega t minus r by c equal to cos of omega t minus r by c cos of omega d by 2c cos theta. This is total because of cos formula, cos a plus cos b. Now apply second approximation, that is d is very less than the emitting wavelength, where d is the length of dipole and lambda is the emitting wavelength. Another way described the second approximation is omega d by c equal to 0. In other words, cos of omega d 2c by cos theta equal to 1. Now substituting equation 7 and 9, this equation 7, this equation 9 in equation 3, then we get this long equation. After simplifying, we get scalar potential equation like this. So we have scalar dipole due to oscillating electric dipole will be given as a function of r, theta and t. We need to apply the third approximation here, that is field point is very long as compared to c by omega. In our equation 10, first term varies as 1 by r and second term varies as 1 by r. While applying third approximation, we neglect any term that vary as 1 by r square. Therefore, scalar potential equal to minus of p naught by omega 4 pi epsilon naught c cos theta by r sin omega t minus r by c. This is scalar potential due to the oscillating dipole after applying all of three approximation. Then there is a current flowing filamentary wire due to the harmonic exchange of charges. We find that the vector potential due to the dipole is vector potential equal to mu naught by 4 pi minus d by 2 to d by 2 k unit vector I dz by r from Maxwell's fourth equation that said that exchanging of charges here d is the dipole length, then I of t equal to dq by dt equal to minus omega q naught sin of omega t, since q of t equal to cos omega t. Then after solving this we get vector potential, then fields due to an oscillating electric dipole. We know these two equations very well. This is electric field equal to minus of del phi minus of del A by del T, and for magnetic field equal to cross product of a vector potential. Calculating electric field. We have scalar potential from equation 11 as phi of r theta t equal to p0 p naught by p naught omega by 4 pi epsilon naught c cos theta by r sin omega t minus r by c. Then del of phi equal to del phi by del r into r vector plus 1 by r del phi by del theta vector. Then differentiate this equation with respect to r, we get this term, and for this differentiate with respect to theta this equation, we get this. Then second term is varying by sin theta by r square, therefore neglecting 1 by r square, we get this term will cancel, only this term will be considered, which is cos theta by r and cos of t minus r by c. Then we have vector potential equal to, then differentiate vector potential equation with respect to t. Then electric field equal to minus of del phi minus of del A by del T. From this term we have found here, this term we have found here. Then put this equation in equation electric field. Therefore we got the electric field generated by oscillating electric dipole. Then Similarly, calculating the magnetic field, which is the cross product of A vector. From equation 14 we have scalar potential equation. This the curl of vector potential will only contain the azimuthal term, where a theta is the mu naught p naught omega by 4 pi r sin omega t minus r by t, and a r equal to minus of mu naught p naught omega 4 pi r. After calculating this, we get expression for magnetic field generated by an oscillating electric dipole. Then finally put the magnetic field expression and electric field expression in Poynting vector. Then we get both the calculating. After this we get this square. Now the intensity of the radiation will be the time average of Poynting vector, like this. This is the total intensity of oscillating electric dipole. For total power radiated over a surface,